Hello everybody, welcome back. We're going to be solving this problem using method of joints. If you haven't seen my previous video, it's going to show you everything you need to know about method of joints. So just click the top right if you haven't seen that yet. But if not, we're going to try and solve this problem as fast as possible. So determine the force in each member of the truss and state if the members are in tension or compression. So the cool thing about this problem is that, the shape of this truss system is actually going to give us a special triangle. If you consider this 8 meters as 4 meters and this 6 meters as 3 meters, we're left with the 3, 4, 5 triangle, which is going to help us a lot for this problem to solve for components in the diagonal direction here. The supports, once again, similar to last time, we actually don't need to focus on them right off the start because we know that they're not going to be important to the actual final answer. We're only looking for member forces, right? So where I want to start first is usually this D member here. Because if you remember from before, we have two unknowns, right? And we have a force applied. So that's going to give us a good starting point. So the first thing that jumps out at me is we need to draw our system at the joint, our FBD. So we have the 600 Newton force applied in the negative x direction. And then we also have two other components here, the FDC component and the FED component. And we remember we also have that special triangle that we can work with there. So the first thing that jumps out is we need to solve for f at x. Why do we need to solve for f at x? It's because we have two y components that are unknown right now, but we only have one x component that's unknown. So we're going to solve for x first. And this is going to give us negative 600 newtons here. But then we also have to consider the FED component of x. So we're going to take 3 over 5. Why do we do this? Because the 3 over 5 is going to give us the x component based on the special triangle. Solving for FED, we will be left with a 1000 Newton member force, and this is going to be in compression. Why? Because we drew it pushing against that joint, and the signs cancel out, meaning that our assumption was correct. Next, we need to solve for Fy, just to get that other component. So we know that FDC is going down, so that's going to be negative. We have the 1000 force for FED, and it is positive because that y component of it is going upwards. And it's going to be multiplied by the component for y based on the special triangle, right? And this x component is relevant to this part, so we're just going to be solving for FDC. Our assumption is correct because when you bring it over, the signs cancel out and we're left with 800 newtons. And this will be in tension because we are pulling away from that joint instead of pushing. Next, we can move on to another joint. So now, if we look over here, we have two unknowns now. This member is known, and we have a force applied. So it's a great place to move on to, right? So we have that 900 Newton load. And the FDC was drawn this way before. So if we go to the opposite joint, we're going to draw it in the opposite direction. We have the FEC component. And I drew this way because I'm assuming that it's going to be acting in the opposite direction from this 900 Newton force. And then we also have the FCB component. So now we can go ahead and solve for summation of forces at x, but you can also take y. Either one is fine to start with because we have one unknown for x and y, and we can just proceed with solving it. So we have that negative 900 Newton there, and then the positive FEC. Solving for FEC, it will give us 900, and that is going to be in which type of force? It is going to be a compressive force because we're pushing that joint. Fy, it's going to be a similar process to solving. We are left with the 800 that we solved from before, minus the FCB, and FCB is going to equal 800 newtons. Those signs cancel out, and it is pulling that joint, meaning it is in tension. Now for this next part, I'm going to start on a separate slide so that we can actually explain what we're solving for. All right, so I moved on to the last joint E so that we can find AE and BE. When we first draw the free body diagram, it may seem like we have a lot of unknowns that we can't solve for. But when you move over to the actual plug-in values, you can see that we have the 1000 and the 900 here. And we have two unknowns to solve for. But if we remember, if we have two unknowns, all you need is two equations to solve for it. And we have our equilibrium equations f at x and f at y to solve for this problem. but there's two components to each of these forces. So the only issue with this is that we're going to need to use substitution in order to solve this problem. So I'm going to quickly go through what the algebra is going to look like, and we can solve this together. All right. So let's see why this is so tricky. So let's do our x components first. We have FAE, and we have our special triangle that we can still work with. So we know that we have FAE 3/5. Moving on, we have FBE, which is also 3/5. And the way it's drawn, they are both in the positive x convention. We have the minus 900 Newton force. We also have the minus 1000 Newton force times the component of the x with the special triangle here as well. You just have to remember that for all diagonal components, you need to consider that there is going to be something you need to multiply it by in order to get that x or y component. So when you solve this algebraic mess, you're going to be left solving for either FAE or FBE. Doesn't matter which one you start with, but if we solve for FAE first, you're left with negative FBE plus 2,500. So in the next equation, we can plug in this equation for FAE in order to solve for FBE. Our next equation is going to be Fy equal to 0. And if we look at what we got, we are going to have another mess of a problem here, but we have the negative 1000 here, which is coming downwards, and we're using the 4/5 for that y component. Next, we have the positive FAE as we've drawn it here. Once again, considering the special triangle, and similarly for FBE, we need to do the same. All right. Plugging in this equation into here. So let me make a note 1. So now sub 1 into there. We're going to be left with an equation that looks something like this. We have negative 800 minus 4/5 FBE plus 2000 minus FBE 4/5 again. And then solving for FBE, you will be left with 750 newtons in tension based on the way you solved it. I know it's in tension because the signs are correct. We have positive on both sides, and the way we've drawn it is pulling away from that joint. And then now we can sub FBE back into this original equation here for FAE, which is going to equal negative 750 plus 2,500, all in newtons. And then FAE, let me see if I can squeeze this in right at the very end, is equal to 1,750 newtons in compression.